All right, so we're going to kind of switch pages here, but we're still going to write down a few things about every particle, the symbol, the definition, and an example. Okay, so we'll switch over, and you're going to write the symbol. All right, for all of those.
Okay. So here's a slide over here that shows alpha decay, and the symbol of that, Coach Forster?
That is a helium particle, which is 4,2 He.
Okay.
The definition, I think that may be on the next slide here. But let's write down this example here first. So we have U238, U92, and it's going to undergo an alpha decay. So it's going to give off a 4,2 helium particle, and it's also going to give off the difference there. Okay, so on the left side, my top number is 238. So I want a number that when I add 4 to will equal a total of 238. So what do you think that top number should be?
238 minus 4.
238 minus 4?
234.
234. All right, and then the bottom number is going to be 92 minus 2.
Would be 90.
90. So we're looking for element 90.
The element is T, capital TH.
TH.
Thorium? Is it thorium?
Yes,
That's
thorium.
what I was thinking. But.
Thorium, yes.
Okay, let's
like the movie. Not really, but...
and so there you see the full
equation. They're working it out over here. So
equation.
they got what we got there.
They haven't quite put the element in there yet.
Haven't quite put the element there. All right, so there, TH. Okay, so we have that. So we can write the definition is a decay that gives off a helium particle. Okay, so it's a type of decay that gives off a helium particle.
Okay.
All right, so let's look at the next one here. So I'll let you guys copy that down. Pause it if you need to copy that. I'm going to get rid of it. Beta decay, and beta is, the symbol for beta is this little 0, 1 minus E. So we have 0, so it has a mass number of 0, and it has a negative atomic number, which is it's basically an electron. So it's the same quantity as a proton, but it's got a negative charge. And it's a beta decay is a high-speed electron that is ejected from a neutron that turns the neutron into a proton. Okay, so neutrons.
It's kind of confusing.
That is kind of confusing. So basically, neutrons are, you can think of as a neutron as a positive charge and a negative charge that just cancel each other out. When it gives off a electron, the neutron becomes, when it gets rid of this, it just becomes positive.
Positive, and so you've created a proton there.
Yep, you've created a proton. Equals a proton is just a positive charge.
So the definition there would just be the neutron creates a proton.
Neutron creates a proton.
However you want to state that. I don't think you need to know it any more in depth than that.
Nope.
Just know a neutron is
creating
a proton. There
gives
giving off an electron to create a proton. If you can fit all that in that little box.
Electron to create a proton. Okay, so let's go to the example on the next page there. Okay, so now
starting out with 131, 53 iodine,
53, and
on the right side you're going to have something there. We'll find in a minute, and then you'll have your beta symbol.
Right,
since it's a beta decay. And so, Coach Forster, your top number.
His top number is going to be not change. Not change. It's going to be 131.
Still 131 because 0 over there not going to affect it.
Not going to affect it.
Now over here on the right, we know minus 1. So whatever we put there, we're going to have to say that number minus 1 has got to be what?
It's got to be 54.
53. You got to be 53. So you need
right.
54.
Right. Well, so you need 54 to be
54
to be accurate
minus
there.
1 gives you 53.
53.
So your new element. Probably made a really loud noise for these guys. Element number 54 is xenon, Coach Forster.
Xenon XE.
It's early.
It is early. So xenon XE. Okay, so we have that, and let's go to the next page. Let's see if we got it right here.
Hopefully we did. 131.54.
Xenon.
Okay.
Okay, so that's the example for that.
That's a beta. Here's a positron emission is the next one.
Positron is just the same exact symbol as a beta, except it's a positive one E, not a negative one E.
So the same thing's happening. The neutron is just ejecting.
It's ejecting a positive sign this time.
Okay.
So then,
I'm sorry.
Oh. Yeah, so it's the same thing as previously. It's just kicking out a proton instead of an electron this time.
And so your definition there would just be kind of you guys can probably figure out that
right
definition.
here.
Neutron ejects a proton is kind of the definition. So you guys can just write that down in your box over there. Here's our equation. Fluorine with a mass number of 17, and of course its atomic number is 9. And Coach Forster set up our positron symbol over there. And so again, our top number, what's it do?
It's going to not change at all. It's going to be 17 still.
Don't change at all. The bottom number, whatever plus 1 has got to equal 9. So what's our bottom number?
Got to be 8.
Got to be 8 plus 1 would equal 9. So atomic number 8 is oxygen. Right?
Good old element 8 is oxygen.
Good old
oxygen. All right, so hopefully you're kind of getting the hang of these so far, and it's pretty simple, not too tricky at all to figure things out here.
Okay, the fourth type is electron capture.
Okay, electron capture and beta have the same symbol.
Same symbol.
Except you notice one's on the left side of the equation.
Okay, and again, your definition's there in blue. You can pause and
write that
down.
The proton absorbs.
Go ahead.
Sorry. Proton absorbs an electron, turns it into a neutron.
Okay, so that's electron capture. And here's an example of this, Coach Forster. And so 118 xenon.
What ain't the hell xenon again?
ZE.
ZE.
And just notice your symbol now is on the left side of the equation.
Side.
That's the only difference in in electron capture and a beta emission is that symbol is going to be on the left side. So again, our top number 118 plus 0.
It's going to be still 118.
Your bottom number 54 minus 1 gives you what?
53.
53, which is we're back to iodine. Earlier.
Yeah, going in circles here.
All
right. So pretty simple there.
We got it right there.
Got it right.
Last one was what we call a gamma ray emission. Coach Forster, you want to?
Yeah, gamma ray is basically it's the most powerful type of radiation because it has no mass.
This is really when you have like a nuclear reaction or a nuclear bomb or something like that. These are really the dangerous ones.
They are
because they can penetrate into almost anything.
Yes.
They're like alpha particles are very massive. Okay, those are easy to be stopped. And you can stop an alpha particle by like a sheet of paper.
Yes.
But these gamma emissions are very,
very small and very, very high powered. So an unstable nucleus is immediately after any type of decay. It always gives off some amount of gamma radiation, which it kind of just depends on how much or how radioactive the atom is and all that. But it increases stability after that energy is released. So when you release large amounts of energy, your stability increases.
And so probably a good definition for you guys here would be right here in the middle where it says emits high electromagnetic radiation to reduce energy. That's its purpose, is to reduce the energy.
And make it more stable.
And that creates very powerful reactions a lot of times.
All right. So we really don't have any example as far as...
because it doesn't affect the actual
equation
any. Okay, so
it's the same mass, it's just giving off energy, lots of energy. So those are the 5 types of decay, and those are what you're going to use on the next page in the notes or in the practice problems to write the equations out. So refer back to this table when you're trying to write out the equations, and remember you're just adding and subtracting to figure out what element is created after these nuclear reactions.
Okay, we'll see you guys later.
All right, we'll see you next time.